And we are ready today to set up the scale-up reaction and to isolate the product. This is always a big step in a project. Once you have identified the optimized conditions, and we did our base screen and we figured out that sodium phosphate was the most effective and chemoselective base for the reaction. And so now that we have our conditions, we know which base to use, we are ready to set up the larger scale reaction and get that product so we can isolate it, make sure we're making the right compound, and gonna get all of our tools ready here for the glove box. Syringes. Tweezers, spatula, grab a couple of extra caps, and the last thing we need is vials. I keep those in the oven so that they stay dry. As soon as I take them out of here, they're going to be exposed to the humidity. I always do this as my last step. And so yeah, once I get these vials out and I get them on the tray, I go right to the glove box. I just go immediately there. So we have our knob here, we'll turn that to refill. I'll go back and forth 3 to 4 times, and on the very last time that I go to evacuation, that's when I'll let it sit for a good 10 to 15 minutes. Now you might be asking yourself, Sam, you're doing an isolation. Why did you set up 4 different reactions for the substrate? The reason I set up 4 is because one of them is going to be my analysis reaction. And what I mean by that is, that's the reaction that I'll quench with water, and I will analyze it by NMR. I will take TLCs, and I'll kind of use that as my kind of throwaway reaction to assist in the isolation of one of the other ones. The reason I have 3 more beyond that is because one of them is going to be my first isolation, right? I'm going to isolate it for the first time. I've never run the column before, and I don't know if the column's going to work. So sometimes your first isolation doesn't really go very well, and you use that isolation to learn how to better do the isolation. So for instance, you might run the column and you find out that there's a really close spot that maybe you didn't see on the TLC, or maybe the separation on the column wasn't quite as good as you wanted. And when you're doing isolations, we typically do them in duplicate, so that gives you one chance. So analysis reaction, first chance at an isolation, and you kind of have some buffer here. If you screw up, it's okay because you still have 2 more. Now in an ideal world, you only have to isolate, 2 of them, and one of them never gets used. Here is the photoreactor. And what we've got going on here, I'm going to put on these safety glasses. These are orange glasses. They block the blue light from coming through. So we'll put those on. And what we've got going on here is a little vial holder. And we'll put the 4 vials in here, put them under here. And the reason I do that is because it ensures that you put the vials in the same place every single time. Same distance from the lamps, and it's all uniform and consistent. Moving it left or right, forward or back, even a little bit can lead to some pretty different results. I've got a fan here, so I'm actually going to turn that on now. Just plug that in. It's pretty strong. And before we turn the lights on, I'll put the reactions in here and make sure that the stirring is going well. Okay, everything's looking good. And we'll turn the light on. So our scaled up reaction should be done. I'm going to take it off, and I'm going to put these orange safety glasses on as usual. You can check it out. Okay. Everything is looking good. And we are now ready to run the column and do the isolation on these and get that product out of there. And it is now time to isolate the product from the scaled up reaction. We've removed the reaction from the scale up setup. And now we're going to do a TLC analysis to see what kind of column condition is going to work for this reaction. So what we need is a standard of the product, or of one of the starting materials rather, which I've got right here. And we can put this just a little bit into a vial. And you only need a teeny bit here. And what we want to do here is we want to make sure that in our column conditions that the starting material does not overlap with our desired product on the TLC. so that when we go ahead and isolate this, we know we're going to get some clean separation. Got my development chamber right here. Got a spotter. So we're doing 3 plates and 3 lanes. The middle lane is going to be mixed, a mixed spot between the starting material here and the reaction. The rightmost lane is going to be just the reaction, and the leftmost lane is going to be the starting material by itself. We'll start off here with 30% ethyl acetate and hexane, and we'll just see what that looks like. So let that run, close this up. And while that's running, we'll actually transfer our reaction that we're going to isolate into a vial. So we'll just transfer this. I'm going to do a lot of shaking. Make sure I get absolutely everything out of this vial and into the bigger vial. And you'll notice here that I did not quench this reaction. I did not add my aqueous solution. And so I only do that quench for the reaction that I want to analyze by TLC or NMR or gas chromatography. But if I'm going for an isolation, there's no need to quench it, and it makes everything a lot quicker, because now I don't have to do an aqueous workup with a SEP funnel and get out my drying agents and filter and rotovap. All I need to do is transfer one of these reactions and its entire contents into the vial. And when I run this through the flash column, all of those solids and all of that leftover copper and all those salt byproducts that I'm getting rid of when I do an aqueous workup, they're going to get caught in the silica. And so they're not going to pose any problems or any issues for our workup. So this TLC plate is just about done. Okay, so we have our starting material right here. Looks like we have some starting material left over in the reaction. We do have a new spot that's coming up above the starting material. And of course we've got our baseline. And there isn't really much above that. So I might just give 4060 a quick check to see if the separation is any better there. Because that separation is not ideal. I could have a little bit of some mixed fractions at the tail end of my product band, because that difference in RF there is not huge. So sometimes if you use a more polar eluent, you can exaggerate the separation that you have. So we'll do that, and I might check 20% too at the same time, just while I'm here. If you go lower in polarity, sometimes that bottom spot will kind of be more affected by it and won't move almost at all. But our top spot, perhaps, you know, in some cases, will still feel the force of the eluent. So we'll just check that too. And while those are running, I will check my stock here of test tubes. It looks like I've got plenty. I will check my eluents. So if I do end up using 30%, I don't really have much there, so I'm gonna have to make some of that. I do have some 20% here if I need that, and I've got some 40%, so already made. I might make up a batch here of 30%, just because I'm guessing I'll probably end up using that one, based on what I've seen so far. So here's our 40% plate. We'll see if that delta RF is exaggerated. Most of the time it doesn't really work out that way, but sometimes you get lucky. So in this case it actually looks like they almost got pushed closer together. So that 20%. And now we'll see if this one exaggerates that delta RF. Oh wow, really not. In fact, they're really close together on this plate. So this is kind of what we've got going here. 30% honestly looks to be the best. And we're ready for our dry load. And I use Celite, and I do tons of Celite here, it doesn't matter. Looks fine. Rinse that down. And the reason I'm using Celite for this dry load instead of silica gel, which you can use either, or you can even use mixtures, is because Celite does not have any polarity associated with it. I think it's not small enough for there to be any meaningful interactions with your analyte molecules. And so it doesn't have any resolving power. And so you can use as much as you want, and it's not going to hang on to your compounds like silica does. And I really get the spinning going as fast as I can here, so that I can get a nice uniform drying. What I'm going to do is load up this column while that's rotovapping over there. So we got our silica gel, we've got our eluent, okay, so here's our dry load right off the rotovap. Give it a couple taps to kind of knock down any loose stuff. And you want to take this off carefully just to make sure that nothing blows around. And I always start by scraping the Celite very carefully out of the kind of the top part of the lid here. And I just work my way . Okay, so we have our Celite dry load all loaded in there, and then I'll put a little layer of sand on there, just mainly for protection when I pour the eluent in. It'll keep everything at a nice even layer. And I like to check the progress of the column as it's running. So I have this little grid plate here that I've made. And what I'll do is I spot every fourth test tube as I'm running the column. And I get kind of a semi-live view of what spots have come out yet and which ones haven't come out. And in this case, the very first spot I should see should be my desired product spot. Okay, so we've run our column and the product has completely eluted out, so we can be rest assured that we've gotten everything. And we did a little bit of TLC of some of the fractions to see where the product is. And so first what we did here is I subjected my grid plate to the KMnO4 treatment, and sure enough we can see that the spot is in row 10 there. And so then I actually ran one of the plates at 30%, and sure enough we can see those spots in rows about 8 through 11. And so that's what we'll focus on collecting. It looks like our 30% ethyl acetate and hexane worked really well. We got some really good separation there. Okay, so we've transferred our fractions to the round bottom flask and we are ready to rotovap this. Okay, so we've transferred our product from the round bottom into this little vial, and we will dry it on the vacuum line to remove all of that residual solvent once it's rotovapped down, and from there we'll be able to analyze the product. Okay, looks like it's done.